then again, if you can trigger exceptions, it's like we said before, if you're using PCRE for your stuff and you have PCRE compiled for Unicode, if you have FF or FEFF in the string that you're sending through, the PCRE is going to say, hey, that's an invalid character. I'm going to stop processing it, and I'm going to say it's not a match. Even if somewhere further in the string is the evil stuff that you're looking for, the PCRE, if it's compiled with Unicode, is going to say, hey, stop. This is not bad, and it's going to continue on. The IDS will let it pass straight through. Then again, you can get into things like recursion. If they implement recursion in their regular expression engine, you can trigger that. And the other great things, you can inject termination characters. If they handle new lines differently, they say, hey, look for this up until the new line, and the server implements new line checking in a different manner. You're going to attack the pattern matching directly that way. So an example pattern matching that's implemented in an IDS currently shipping today is what you see now. It's a very simple search. So what it's doing is you have your packet data that's coming in, and you have your string that you're looking for inside of your packet data. So what it does is it walks through the packet and says, okay, at this byte, does this string match? Moves forward a byte. At this byte, does the string match? Well, so the example how you would use it, you'd say, hey, search for data, which is this size, for the string, the evil foo bang, which is 8 bytes. So how do you attack this? You maximize the work that search function will do. So if you send evil foo does not match evil foo bang. So if you send evil foo times 8, what that's going to, when you look at it, there's going to be 48 different calls to memcopy. Depending on the implementations of memcopy, you can have between 96 and 388 actual memory operations for reads and compares, which evaluates to, on a 65K packet on a 3 gigahertz box, it evaluates to 200 milliseconds for a 65K packet of just evil foo without the bang. Again, forcing the IDS, like we said, you had to process like 3.2 packets per millisecond. Well, with one packet, you can make it take 2,000 milliseconds. Again, cause the IDS to stop. It's spending so much time handling this single packet. All the other ones in its queue, if it's in the let it go through, if I can't keep up, they'll let on that through. Again, this is all dependent on platform alignment and the libc implementations of memcopy, but there's an IDS currently shipping today with this search algorithm. So one of the other things you can do, a number of IDSs are using PCRE, both in hardware and software. PCRE has a number of implementation issues that have to take into account. So one of the IDS rules that's currently shipping today on a certain IDS is looking for a from where they don't have an ampersand within 655 bytes. So what is this regular expression? For those of you that don't understand regular expressions, this is what it does. So you see the dot star. That says match any amount of data, as much as possible, up until from. And then you say, I want to match from equals. So yeah, simple, that should be self-explanatory. The next part is, I want to see at least, if I see 600 or 165 characters that are not ampersand in a row or more. So if you see more than 165 characters and an ampersand. And then, so what it will do, it'll process that data over and over and again. So how do you force the backtracking? So if you say from equals over and over and over again, and then every 165 bytes you insert an ampersand. Well, none of the froms are going to match, but the regular expression engine has to check every single from equals to, scan forwards at least 165 bytes and look for an ampersand. If it doesn't see an ampersand, it says, okay, now go to the next from. Well, if you insert a whole number of froms, you can make that take forever. We'll go ahead and do a quick demo of that.
That particular signature is looking for a HTTP URI request where the from parameter is longer than 165 bytes. So just to put it in context, that's just a GET request. Right. You can do that with any telnet client if you type it out. All
right, so we're going to go ahead and take this regular expression. So great tool for those of you writing PCREs. The guy that wrote PCRE has a tool called PCRE test. You evaluate a regular expression, and then you can provide data to it. Well, there's a timing mode for it. There's that -t. It'll tell you how long it takes to process. So normally, what will happen is if I just do from and then ampersand, it'll tell me how long it took to execute. So if I did the from and then an ampersand, it responds in less than a millisecond. So that's okay. So what if we do the worst case attack? So go ahead and cut and paste this. And we'll wait and wait and wait and wait and wait and wait some more. Unfortunately, the guy who implemented PCRE test didn't think that any regular expression would take more than a millisecond to respond. So his accuracy in his calculation is kind of slow, or it's kind of wrong.
So that's definitely greater than 3.2 milliseconds.
Right.
Just to.
And again, this is on a simple GET request, and you can, very simple. Go modify Apache Bench to send this going across your wire. You can send thousands upon thousands of these a second across, a 10 megabit IDS, and make, they take 5 or 6 seconds per packet instead of, 3.2 packets per second.
And this is a NetScreen IDP appliance, just in case anyone's wondering which appliance you can hit with this.
Which one's the presentation? All right, and then again, one of the things you have to do is you can attack the signatures directly. So again, how does the IDS handle something differently than the end host? So one of the things that's really interesting to handle. So very recently, Snort had an evasion announced in it.
Had?
How it was handling.
Had?
Had an evasion in it for how it handled spaces in separating a URI. So between the GET and then the actual URL. So the /CGIBNPHS. So the way it handled spaces was it looked for a space, and depending on what configuration you had for the HTTP inspect, it would look for a tab instead. Well, unfortunately, IIS also supported, for the specific IIS version that was released publicly with the advisory, also supported tabs, new lines, a vertical feed, a horizontal tab feed, and then a control feed, or just regular spaces. And then how they handled the new lines was also different. So a number of different web servers also supported just control the /r instead of both just /r/n.
A quick thing on the ISpace issue. The reason why ISpace is such a big problem is that every Apache server out there supports all these different forms of space characters, and Apache also will basically eat any white space between the beginning of the method, the URI, and the version. And there's no real limits on that besides the maximum request of the entire request buffer. So if you actually pad this out with 256 bytes of random space sequences made up of that character set between the GET request, the URI, and then the version, you actually bypass, I think, 4 out of 5 IDSs I tested using the same string completely. I know I've tested Tipping Point, I've tested probably an older version of Snort, I'm not sure what the current status of that is, a NetScreen, IDP, etc. But basically changing all of the attacks that I work on at my day job to use this type of space padding, bypassed 4 out of the 5 IDSs there, and the last IDS noticed, hey, something's really screwy, and dropped it. But it didn't drop it because of the spaces, it dropped it because it just looked like a bad packet.
And then the other thing you can do is if they're using something, a number of the public pattern matching APIs have limits. So for example, the from example that we gave, the attacking PCRE directly, well, a number of the IDSs use things that say, hey, if I had too much recursion, stop processing it and say, okay, it's good, let it through. So if they, how much malloc data they're going to malloc before they say stop and processing and go through. Well, a number of them are set up badly. So when they hit their max limit, they just stop processing it. So there's a certain IDS vendor that publicly right now, if they recurse more than 7 times, they say, okay, I'm spending too much time processing this, just let it pass.
So add a quick prefix to every one of your web requests, and now every one of them bypasses that IPS. Kind of a neat thing about doing signature discovery is trying to figure out what signature a vendor has for a specific attack. And you start off with saying, okay, here's an exploit I know of, now let's change a byte, now let's change another byte, now let's make this byte bigger, longer, change spacing, change padding, and so on. And you can actually create kind of a black box signature detection tool for any given IPS or IDS products. And if you have an IPS, it's great because you know whether it detected it or not based on whether it dropped the attack. So it's really easy to say, yes, it blocked it, no, it didn't block it. You don't have to actually pull the event engine, anything like that. So a nifty thing you do is basically disable the block mode or enable the block mode in the IPS, make sure there's no anti-flooding or rate limiting stuff set up in the IPS, and basically to start permutating each character in an attack, starting from the left to the right, and then from the right to the left, and then doing both at once. And you can find out exactly what the minimal chunk of the data you're sending matches as a signature. So it allows you to basically extract the PCRE or the regex from any signature using standard kind of black box testing techniques. And it's interesting because you can also use things like hardware monitoring to figure out where the loads are. So you start sending one type of request and then slowly permutate that request different to longer or wider or different types of characters, and you can kind of figure out where the bottlenecks are on the appliance. Hardware bus monitoring, if you actually want to get crazy with a scope and actually monitor how much data is going across a certain bus, you can use that to actually figure out where the attacks are if you have a logic analyzer and take the box apart and all those kinds of fun things. Also, you can just root the box and dump the process and kind of monitor it from there, which is much easier to do in certain appliances, especially some that give you root access or protect it poorly. Finally, a lot of people are actually using encryption signatures now, or excuse me, encrypting their signatures as part of their appliance, and a lot of them aren't doing a really good job of encrypting those. So as soon as you pop that key, now you have access to every one of those signatures, and you can design an attack specifically to evade that particular IDS and that signature. So kind of a conclusion for this, our statement is basically everything can be avoided, everything can be evaded no matter what. It doesn't matter what appliance you're running, it has limits. What software you're running, it also has limits. What the attack is, it has limits. The questions really are, what layer can you evade it? How much does it cost you as an attacker to evade it? And how much time do you have to spend, and at what speed can you do the evasion? Those are really the limiting factors. You can guarantee evasion at just about any IPS or any kind of security product. It's just a matter of figuring out where the balance is between, how fast does the attacker have to send packets, how much data do they have to send, and how sophisticated do they have to be able to do this type of attack.
All right. Again, our contact information. Any questions?
Yeah, we can do more demos if you want, but I figure you guys want to eat.
Yeah, because we're like 15 minutes over time.
Sure.